Hey P-Stats, just got done watching tonight's episode of The Bachelor. It was great, can't wait for tomorrow night, the actual season finale, and we're going to get you guys, now that I'm free, we're going to get you guys started and ready to go on this new chapter. So, we're going to kind of move away from, in the last chapter we were doing all sorts of inference about proportions, and we're going to kind of move away from that. So if you grab the notes packet, hopefully the sub has passed it out, grab that notes packet. Now we're going to take a look here at reminding ourselves we already know about sampling distributions for means. So if you read through the top here, it says if our data comes from a simple random sample and the sample size is sufficiently large, then this is what we learned at the way beginning of part 5 of the class. It says then we know that the sampling distribution of the sample means is approximately normal, and that mean is supposed to be at that population mean. And the standard deviation, you take the population standard deviation and divide by the square root of n. So hopefully you can kind of remember back to all of this that you already know about sample means. It's been a while, but it did come back up on your final. I think some of you did review it with me yesterday. So hopefully those two things are feeling familiar to you. However, we have a problem, right? Because in that chapter 17, I believe it was, we were talking about sampling distributions. A lot of the times we were making this sampling distribution knowing the population parameters, and that's not really realistic. We don't normally know population parameters. So the problem here, if you look, is that our standard deviation is unknown. And so we can't calculate a standard deviation for a sampling model because I don't know what that population standard deviation is, that sigma. So what we're going to do is we're going to estimate the value of sigma in order to use the methods of inference that we've learned so far. So in order to use a distribution to kind of model what's happening and then make some inference from a sample. So we're going to have to estimate that sample or that population parameter standard deviation. And we do that by using S, as you can imagine. So we're going to use our sample standard deviation to estimate sigma. And so what happens then is when we go to do our test, we're going to use, in our standard error formula, we're going to use, instead of sigma, this S. So I'm going to try to point to it here. We're going to use this S here from whatever sample that we collect. And so that's going to be what we use instead of sigma. Otherwise, the formula looks exactly the same. You still have to divide it by the square root of n to adjust for your variation decreasing as your sample size increases. So that's our standard error formula. So then if you look at the next paragraph, it says, however, if we're replacing sigma with a sample standard deviation, then our statistic now is more variable. I don't know that population parameter. I'm using a smaller sample than the entire population to get these statistics. And so we've got more variability. And so we're no longer going to be using a normal model or a normal distribution to model this distribution. And so we can't call it Z. And so you're finally going to get to learn a new distribution that is not the normal distribution. It's actually called the T distribution. So, oh my gosh, no longer normal. Who would have thought? It's now the T distribution. So instead of finding Z-scores, now you're going to be calculating test statistics that aren't Z-scores. They're T standardized values. But like a Z-score, the T value that you find, the T-score, if you will, tells you how many standard units away your sample mean is from the population mean. So it works and operates just like a Z-score. It's just not for a normal model. It's just for a T distribution instead. And there's a really, really, really interesting story about how this T distribution came to be. You can look it up, or you can remind me and I'll tell you on Thursday what it is. And in fact, on my honeymoon, we actually visited the place where the T distribution came to be, and I'll give you a little hint. It happened at the Guinness Brewery in Ireland. It was actually a statistician that was working for Guinness that came up with the T distribution. So I'll tell you more about that on Thursday if you remind me. It's super interesting. And I took a picture with the little sign with it on our honeymoon, so I'll show you that as well. So your test statistic, your not a Z-score, but your T value is going to happen just the same. You're going to take essentially your sample mean, so that X bar, and you're going to subtract the population mean that we're trying to estimate. So you'll see it, we'll make a null hypothesis. You'll see it in a minute, but we're going to get a population mean. And then you divide both of those by our standard error. So the sample standard deviation divided by the square root of n. And so that's going to be your test statistic. It's not a Z-score. but it's a t value, and we'll talk about kind of what that looks like. Before we do that, let's talk about what the t distribution looks like and how it's different than the normal model. So you're going to see here a picture, and it kind of looks like the normal model in that it's still unimodal, it's still symmetric, has that same bell-shaped curve, but what you're going to notice is it's got more variability. So that normal distribution has that high peak in the center, low tails, and the t distribution can vary in how high the peak is and in how tall and fat the tails are on the end. So basically there's just a higher spread in the t distribution, and it'll change depending on how large your sample is. So when we describe a t distribution, we look at something called its degrees of freedom. And so the degrees of freedom will kind of tell us how fat the tails are and how spread out the distribution is and all of that. So the degrees of freedom for any one sample test statistic is n-1. And the reason for that is I think we've talked about this n-1 before when we were calculating standard deviation by hand earlier in the year, and we divided by n-1 instead of n, and it has to do with the fact that if you think about, like, you've taken all of your tests except for one in a trimester, and you calculate, I've taken 3 out of the 4 tests, and if I know the score that I'm shooting for, like if I'm shooting for a 90% in the class, I can figure out exactly what I have to get on that last test in order to achieve 90%. So while it's unknown what I'm going to get, I know what I have to get to achieve a certain goal. And so there, in a set of n, there's only n-1 things that have variability, because once I have all those n-1, there's one left that's a constant, and it's set, and it has to be this because it's the one that's left over. I don't have choice in that one anymore. So that's why the degrees of freedom is n-1. And when you look at a test and you see your sample size, you're going to have to identify the degrees of freedom because they have a great effect on what the distribution looks like. And so if you look at that model on your notes, the solid line is our normal distribution that we know well. The second one you see is a t distribution for a sample size of 10. So it'd be 9 degrees of freedom. And it's got fatter tails than the normal distribution. So you can see here that the center is dropped farther down. So there's less values that fall in that middle of that distribution. And if you look at the dotted tails over here, they're a little bit higher on the edge than they are for the normal distribution. So there's a few more data points that live in those extreme values than for the normal, than what we're used to. So you're going to see me kind of highlight the sample size of n shape there, so you can kind of see what that looks like. Now, if I go even smaller, if I do a sample size of only 2, then the t distribution gets even more variable. So you're going to see a shorter peak as well, and kind of the fattest tails of the 3. And so you're going to see even more values living in those extreme values, and less that are sitting right on that population mean in the very center. So there's less that hit it, and more that are even more far away. And so the more degrees of freedom that you have, okay, actually we'll do it this way. The smaller degree of freedom is going to give you the fatter tails. It's going to give you the greater variability. So the less your sample size, the more variability you have. And that should be kind of intuitive too at this point from all the formulas and stuff that you've seen. As the degrees of freedom increase, the t distribution gets closer to the normal distribution, since the sample standard deviation that we're approximating with is going to get closer and closer and closer to that population standard deviation. So, rather than walking through all of the little steps of phantoms and showing you what all the assumptions and conditions are and showing you what the test statistic is and the p-value, a lot of this process is going to feel like what you already know how to do for proportions. And so I want to just do it with an example. So while you flip your page over, we're going to do an actual one sample t-test. I'm going to show you what this looks like. So let's read through this problem, and you see I already did that and kind of was underlining some things and writing some notes down as I went. So let's just read through this. It says, a coffee vending machine dispenses coffee into a paper cup. You're supposed to get 10 ounces of coffee, but the amount varies slightly from cup to cup. In a random sample of 20 cups, we listed the amounts that were measured for ounces of coffee in the cup. And then I'm looking at, is there evidence that the machine is shortchanging customers? So I see a lot of 9.9s there. I see that the lowest is 9.5, but I also see some that are at 10.2. And so basically I'm looking at, is the average less than 10? They're supposed to be getting 10. Are people getting shortchanged? That's what I'm trying to measure. So it's not about success or failure here, okay? I could probably word this problem in a way where I'm looking at how many of the cups, what proportion of the cups get less than 10. But that's not the way that the question is worded. It's asking about what is the average amount of coffee that gets poured into this cup. So it's an average, not a proportion. And so that's why we can't use that z-score and that proportion, that sample proportion, p-hat, q-hat stuff that we were doing before. Now we have to use our new distribution, our t-distribution, since we're talking about means. So what I'd like you to do is grab your calculator. I'm just going to see what happens here when I press play, because I'm curious. Okay, so here's what I'd like you to do. Grab your calculator, and you're going to type all 20 of these numbers into your L1. So have you pause and go do that. Okay, now you're going to pause again, and you're going to calculate the one variable stats. I'm looking for a couple of things here. I'm looking for what is the X bar, so what's the sample mean. I'm looking for what's the S, what's the sample standard deviation, and I'm looking for what's your N. So take a minute. In a second, I'm going to write these down, but run your one variable stats and make sure that you get the same thing that I do. All right, let's take a look here. So when I ran my one variable stats, I got an X bar of 9.845, a standard deviation of 0.199, and again, I already knew this, but the N, the number of things in my sample, is 20. Okay, so we're going to run through the whole Phantoms process just like what you're used to. I'm going to have you pause along the way and try things in your calculator and make sure that you're understanding this so when you go to practice in your homework packet, you've got it down. So we're going to start with the P step, and the P step is to define our parameter. What are we looking at? What are we trying to be able to say something about at the end here? And so our parameters before were P's because we were looking to estimate the true proportion of something. But here, I'm not looking to estimate a true proportion. I'm looking to estimate what is the population mean in this case. So when I write my P step for Phantoms, I'm going to be trying to look at a mu value every single time. I'm looking for that population mean, that mu. And in this case, I'm looking for the mean amount of coffee that's getting poured into the cups. What is the actual amount that the machine is programmed to put into the cups on average? And so that's my population parameter that I'm trying to say something about here. And so when we're doing this mean inference testing, it's always going to be a mu that you're defining, not a proportion like you were before. Okay, so we're going to write two hypotheses, and this step is going to feel really similar, except again we're using this mu instead of p. And so just like before, when you write your null hypothesis, it's always going to be an equal. So your null hypothesis here is that the mean equals 10. That would be boring. That's what they say is happening. Our alternative hypothesis is we're looking at, were people shortchanged? Okay, so is that mean actually less than 10? So we're doing a one-tailed test of less than 10. And so again, your alternative hypotheses here can either be less than, greater than, or not equal to, just like what you already know. We haven't talked about assumptions and conditions yet. They're going to be pretty much the same as what you were looking at for back in Chapter 17 when we were looking at the sampling distribution for means. You want to first look for a simple random sample. So if you go back to the problem, you're going to see I underlined that it was a random sample of 20 cups, so check. Random sample is our first condition. Secondly, I want to know, am I sampling independently here? So is 20 less than 10% of all of the coffee cups that this machine is pouring out? And it is. So I get to keep that independence as well. So those two are going to feel like what you already know. Okay. Third one is tricky. If you remember back to our sampling distributions for means, we were checking, is our sample large enough? And it was very arbitrary. So I'm going to try to give you some rules here. What you're going to have to do every single time is you're going to have to actually draw me a little sketch of what your sample histogram looks like. So remind yourself, you've already got this set of 20 cup ounces in your L1. So what I'd like you to do is go into your stat plot, so hit second y equals, and actually make a histogram of this data. So remember, you're going to go into that stat plot menu. You're going to turn that plot on. You're going to make, when it says type, you're going to make a histogram. And then you want your X list to say L1 and your frequency to just be 1 each. So on histogram L1, 1. And then you're going to press zoom 9 to get that stat plot zoom. Okay, how you want it to be. So go ahead and stop the video and go make a histogram for our data. And to see if our sample is large enough, here's what I'm going to tell you to look for. Okay, so we're going to be checking, is our sample large enough? So I'm going to hop over into the margins and start writing. And it really depends. You're checking to see, does my sample look normal enough given the size of the samples? Here's going to be the general rules I give you. If your sample size is less than 15, you want to see that your data is essentially looking normal so that you're approximating it with a t-distribution is okay. If your sample size is between 15 and 40, it doesn't have to be exactly normal, but you want to see roughly a unimodal and symmetric shape. Doesn't have to be perfect, but you want to see kind of that one hump, and you want to see that it's roughly symmetric. If your sample size is super large, if you got a sample that's 40 or higher, it doesn't really matter what the shape is, because remember, with sample size larger and larger and larger, your sampling distribution comes out pretty normal either way. So you're always going to be looking at the histogram, using your calculator, drawing me a sketch, and then saying, given the sample size, does the shape of it look close enough to normal to matter? So in our case, we have a sample size of 20. And when I made my histogram on my calculator, it looked something like this. So I'm going to actually draw the sketch of it, and I'm going to ask that you guys do that. And it's not perfectly normal by any means, but it's definitely got that unimodal and roughly symmetric shape. So I'm going to put a check mark next to the fact that our sample is large enough given its shape, that we're looking okay here. Okay, so those are the 3 conditions that you're going to want to hit. Once you hit all 3 of those conditions, you can name your test. So this is our 3rd different test that we can run. We had 1 proportion, we had 2 proportion, Z, both of them, because it was a Z-score normal distribution type of deal. But here, my name of my test is a 1 sample t-test. Okay? I have 1 sample of data, not 2, and I'm looking at means, so I'm going to have to use that t-distribution. That's how I know what I'm doing. Once you name the test, you're going to also have to give me the degrees of freedom. So pause, write down what the degrees of freedom here are. So since our sample size was 20, your degrees of freedom should be 19. All right. Next, we're going to calculate our test statistics. So I'm looking for a t value, and I put that little subscript 19 to remind myself of the degrees of freedom. So always remember to put that in as well. When we actually use the TCDF button in our calculator, which I'll talk about in a minute, you have to include the degrees of freedom. Again, because the shape of that t distribution changes based on the degrees of freedom. So I wrote out the formula for you. Why don't you pause and try to plug in the numbers in the places that they go and make sure that you are doing that part correctly. All right, let's check what you did. So I put my x bar minus my mean over my standard deviation divided by the square root of n. So hopefully you did that formula and you got those numbers in all of those places. Again, they're all coming from pretty much over here. Plus that mean is coming from my null hypothesis of 10. Okay, so that mu value comes from your null hypothesis every time. So go ahead and calculate that t-score, and you should get negative 3.49 roughly. And we're going to obtain our p-value. To get your p-value, this is where you normally would do normal CDF with your z-score, and you just go from your lower bound to your upper bound. This time we're going to do something really, really similar. So grab your calculator, press second vars, and go to TCDF. So I think it's like option 6 or something near there. And you're going to do roughly the same thing, where you're going to do TCDF. You're going to give it a lower bound and upper bound, and then you've got to give it the degrees of freedom. So in this case, I'm trying to do a less than test. So I'm going to go from negative 1,000 to negative 3.49. And at this point, you're expecting a really, really small number because you're used to the normal. It's not going to be probably quite as small as you're anticipating because remember, we've got those slightly fatter tails on the ends. But you're going to type that in, hit enter, and you should see a p-value around 0.0012. Now, if you did a z-score from negative, if you did like a normal CDF from negative 1,000 to negative 3.9, it would be smaller than that. But this is still relatively small. So the question I'm now faced with is, do I have the 0.12% of samples where the mean is actually 10, but I just got a really crappy sample? Or do we actually think that something else is going on? Generally, I don't believe I'm that unlucky that I would get the sample that only comes up 0.12% of the time. So I'm going to make the decision to reject the null. So we're going to go ahead and write our conclusion and pause. I'm thinking you would be able to do this without, but why don't you pause, try it, and then check the conclusion that you wrote. All right, so let's check. So this is what my conclusion ended up looking like. And again, you're going to see me start to get lazy and put the M and the S together in one step. So since our p-value is low, we're going to reject the null hypothesis. There's sufficient evidence of the alternative hypothesis, which is there's sufficient evidence that the mean amount of coffee per cup is less than 10 ounces. And that's what this test has taught me. I gathered this sample. I found out that the mean amount of coffee per cup is likely less than 10 ounces. And that's how you do those tests. We're going to talk about intervals on Thursday, so you can hang tight on those, but grab your homework packet and try to find a test or two that you can do to kind of see if you've got this. And then we'll, of course, go over it on Thursday and talk about intervals as well at that point. Hope you guys have a good couple of days, and I'll see you on Pi Day. Bye, guys.